Hello again, here's an A-Level Further Maths video. We've reached chapter 2 of the Core Pure Mathematics book 1. We're going to introduce ourselves to something called Argand diagrams. Now in chapter 1 we learnt about imaginary numbers and we learnt about complex numbers. What I'd like you to do is just very quickly spend a few seconds thinking about the question on the screen here. I've put a number line. Now all of our real numbers can fit on that number line. We've got positive numbers, negative numbers, and so on. Is there a natural place on that number line to put imaginary numbers or complex numbers? What do you think? Well, the simple answer is no. There is nowhere we can put our imaginary numbers on this number line here. There is nowhere we can put our complex numbers on our number line here. So how do we deal with that? Well, let's see if we can have a look at a number line here. Now this is where we have our real numbers. So for example, the number 1, I've written it there as 1 plus 0i, but there it is on our real number line. I can sort of find, bigger numbers here. We can go down to negative numbers here. And this is what we're used to seeing here. So there I happen to be at the number minus 5.32. So what do we do then when we're trying to find our, a place to put our imaginary numbers? Well, here's what we actually do. We go into the second dimension. We go from a one-dimensional real number line to a two-dimensional space, and we put our imaginary numbers on a vertical axis here. So there, for example, is the number I. I've written it as 0 plus I here. So you can see that we've actually sort of gone away from the real number line and we've taken a journey into the second dimension here. But let's move it up here. We can see, there we go, there's a number there. There's 3i would be just there, roughly. There it is. We can go down to sort of like negative I values down here. So there we are at sort of around about minus 5i there. And complex numbers, which have a real part and an imaginary part, well, they can be accommodated too on this diagram because we can put them sort of over here somewhere. So there we go. It's a bit like coordinates here. So this number here, which is 3.2 plus 3.01i, we just go to the point with coordinates 3.2 and 3.01 up here. Obviously, we can make some of those coordinates negative. So down here, for example, that complex number would have a negative real part and a negative imaginary part. So this is a way that we can actually sort of have a position, if you like, for our complex and imaginary numbers. When we do this sort of thing, when we extend our real number line to a two-dimensional diagram like this, we call that an Argand diagram. It's named after a French mathematician called Argand, who had the idea to do this. Our real numbers live on the real horizontal axis, and our imaginary numbers live on the vertical imaginary axis. And any complex numbers, a bit like coordinates, we can sort of put it on the Argand diagram that way. So let's just make sure we've got that idea. Can you please pause the video in a second, do a quick little sketch and represent the following complex numbers that I've got on the screen on an Argand diagram. Okay then, I've got my graph plotter up here to see if we can get the answers here. So Z1, I think, was the complex number or the imaginary number 2i. There it is. Hopefully you put it up there on the imaginary axis, 2 units up there. Z2 was the negative 4 there. That's a real number, so that lives on our real number line. Z3 was the complex number 1 plus 5i, and there it is up there, 1 plus 5i. Okay, and then finally Z4, we had negative 3 minus 3 over 2i, and there it is right there, minus 3 minus, well, 1.5i there. And so there we have our numbers on our Argand diagram. Nothing too complicated so far, I hope. Right, now let's see if we can just answer this slightly different question, which I put on the screen now. I've given you a complex numbers question, but I've also given you a vector question as well. And what I'd like you to do is find the answers to both of those and then explain why we've got such similar answers in each case. Okay then, let's have a look and see what we've got here. So let's do the complex number question first. So we've got the complex number 1 minus 3i. We're adding it to the complex number 2 plus 4i. And we can do this just by collecting the real parts together, first of all. So 1 plus 2 is, of course, 3. And then if we look at the imaginary parts, negative 3i plus a 4i here becomes plus I. So hopefully nothing too complicated there. Now let's look at the vector situation here. So we've got this vector 1 minus 3. We're going to add it to the vector 2, 4. And then again, we can just look at the two components separately here. So the 1 plus the 2 here gives us 3. Negative 3 plus the 4 here gives us 1. And we have our answer there. So I asked, why are these answers so similar? Well, you can notice, I'm sure you have noticed, that the numbers we've got are basically the same numbers. And for the complex number situation, we had two separate components to it, didn't we? We had the real parts and the imaginary parts. And then the vector situation, we had exactly the same sort of thing going on, two separate bits. You know, we had this sort of x component here and this y component here, if you like. So of course, we're going to get very, very similar looking answers here. And this leads us to a very common way of representing complex numbers on an Argand diagram. Rather than representing them as a point, quite often you'll see complex numbers represented as vectors. So let's see if we can go to the graph plotter here and have a look at these things represented as vectors. So I've actually got the numbers that we were just dealing with here. So in our question we've just done, we had the number 1 minus 3i here, z1, and we had the number z2, 2 plus 4i, and then we added them together to get the answer there, 3 plus i. Now if you think of that in terms of vectors, that would be our vector 1 minus 3. So we start at the origin and we go down 1 minus 3. Now the vector which associated with complex number z2 up there would be that one there. But actually, when we're adding vectors together, we wouldn't necessarily put it there, would we? What we'd do is we'd actually probably put it coming from the vector z1 down there. And you can see that when we bring those two vectors together, it does indeed lead us to the resultant vector there, which is the answer to the question. So the final thing which I'm going to ask you to do in this video is draw a quick Argand diagram. Just do a quick sketch. I've got some questions on the screen there, and I'd like you to indicate where those numbers are on your Argand diagram, but indicate them as vectors, please. Okay, let's have a look at the graph plotter and see what we've got here. So, so the complex number z1, first of all, minus 2 plus 2i, well, there it is as a point, but as a vector, we would just draw that there like that. Okay. The complex number z2 was 3 minus i. So there it is as a point, and there it is as a vector. Okay. z1 plus z2, well, hopefully you got that as 1 plus I there. And as a vector, there we are, just there like that. Okay, so far so good. All right, I'm going to clear those away now, just because it's probably easier to see the last two if I don't have them there. So let's get rid of that now. There we go. Right, so 3 lots of z1. Well, there we are up there. Can you see it up here? Minus 6 plus 6i, so as a vector, that would be this one right here. There it is like that. And then finally, the conjugate of z2. Did you remember what that notation meant with the little star? Well, there it is. z2's conjugate is 3 plus I. But as a vector, there it is there like that. And that is our introduction to the Argand diagram. Quite a simple idea. I hope you agree with me. If you want to get yourself a bit more practice and a bit more stuff to do with, complex numbers in general so far, then exercise 2A is a good exercise for you to be doing. But we'll be back shortly with another video which is going to use the Argand diagrams even more.